Greetings folks, it's Professor Fiore, and in this video we're going to start a sequence that explores room acoustics. What we're going to talk about today is essentially what happens to sound when it goes from one room to another. So I am going to start by drawing a wall. Ugh, not the world's straightest wall. Bear with me. So, doesn't matter. Let's just imagine we got a wall over here. Now I have a sound source. All right, there's a sound source out here. Whatever it is. Person speaking, playing a musical instrument, whatever. Sound emanates from this. And at some point, right, I'll just imagine a single sound ray coming out and it hits this wall, right, this barrier. Let's be generic about it. What happens? Well, basically one of three things can happen. Some of that sound can be reflected back into the room. Right? And so if you've ever played pool, billiards, ball hits the bumper, bounces back in. Right? So that's the first thing. The sound can be reflected back in. We're actually going to spend one video just looking at this, the reflection part. What else can happen? Well, some of that sound energy can come into here and essentially sort of shake around whatever it is that's inside this wall, right? The mechanics of this wall. Essentially what's going to happen here on a microscopic level is that energy, remember, energy has to be conserved, just doesn't disappear. That energy gets turned into heat, right? It's absorbed in the structure itself. All right, and then there's one other thing that can happen. If it doesn't get bounced back in and it's not absorbed, then it gets radiated back out into the other space. In other words, it gets transmitted through for whoever's out here. Transmitted through. That can be a problem. If it's your neighbor, they might get upset. All right, take a look at these first three letters. R-A-T, that spells rat. So there's a nice little mnemonic for you to remember the three things that can happen. All right, and we're going to spend time on each of these. In this video specifically, we're going to look at this last thing, the whole transmitted through business. All right, so, out here, you've got a neighbor, let's say, and I'll draw this with all of the flair of an XKCD comic. And maybe that person doesn't like the sound that they hear because, they're trying to study, they're trying to read, they're, whatever the heck it is, right? Okay. Of course, this goes the other way. If maybe this space over here is something like, recording studio, you don't want sound out here, a bus, an airplane, to come in. That's going to ruin the take you just had. You got a great sax solo and guess what? Halfway through, somebody drove a semi through on the street in front. So that just ruined that take. Got to do that again. That's no fun, right? So we have to kind of quantify this, figure out for various materials what reflects, what absorbs. In other words, how much of what's left over gets through, right? If it's not reflected and it's not absorbed, then it must have gotten through. So there are materials that are very good at reflecting. A painted cinder block wall, for example. 99% of the sound that hits that is going to reflect back in, right? It also has tons of mass. It's very, very massive. So mass is really good at preventing the sound transmission. So, we can have something that absorbs like, heavy drapes, rigid fiberglass, right? So this doesn't have to be something like concrete, but I could have this, whatever it is, filled with highly absorptive materials and not a lot gets through, right? And these characteristics, sound being reflected or absorbed or being transmitted through, this will depend not just on the material, the structure itself, and also things like, frequency. In other words, I can have a material that's really absorptive at 5 kilohertz and is not very absorptive at all at 100 hertz. So it's not as simple as, 95% done. Right? It's going to vary. We have things to worry about here. And to confuse it just a little bit more, we know that the human hearing response is not consistent across the frequency range. Our ears are more sensitive in some areas of the frequency spectrum than in others. So how do we put this all together? How do I quantify just how well the particular barrier, whether it's a wall, a window, a door, whatever the heck it is, how do I quantify just how well that thing works as far as preventing sound getting through, right? The T in the transmitted through, okay? How effective is that, okay? So we come up with, I'm going to clean this up just a smidge. So we come up with something called a sound transmission class. All right, so this is a standard measurement, basically, rating, if you will, of materials in construction. This is typically used in North America. Elsewhere, there is an ISO noise reduction index, a standard for that. And the purpose of that is essentially the same as this, the STC rating. So essentially what we're going to do, just to kind of give you an overview, is we're going to do a little plot. There's a frequency plot coming across. So down here, we've got like 100 hertz, right? And I'll just put some things down here. Here's 500 hertz. Here's 2 kilohertz, and so on and so forth. And on this axis, we have the attenuation in decibels. All right, attenuation in dB. So you can imagine building sort of a test fixture, right? Imagine you have a structure that is, I don't want to use the word soundproof because nothing is soundproof. Soundproof implies that no sound energy gets through, and that's a misnomer. That's not real. But let's say we have something that's pretty darn close to impervious. All right. So here's my room, if you will. And it's crazy, man. It's just insane. And now what I'm going to do is take a test fixture. So maybe I have a window or, a wall or something. So I'm like looking down on this. So here's this wall, the thing I just drew. And what I'll do is stick a microphone in here, right? And I have a sound source back here. And that's going to come in, boom, hit this. And of course, some of the sound is going to come through, right? Transmitted through. Now, since I know there's going to be no flanking sound because of the way I've built this, and there's no structurally born sound if I do this correctly, the only sound energy that gets through is from this test material, right? This test barrier. So I can figure out just how much of a loss there is because I can measure what the SPL is over on this side, and then I measure the SPL on this side. I can figure this all out, right? So I wind up doing this at several frequencies. Now the standard, the SDC standard, I think has 16, if I remember correctly, 16 different frequencies spaced at 1/3 octave intervals. So I would do this, okay, I'll do it at 100 hertz, and then I'll do it at 130 hertz, I forget the standards, but I would just keep repeating this at different frequencies, all right? And we might get little resonance nodes and things like that. But I get this set, right? And I can sort of connect the dots on this. And there's the overall characteristic. Now what we'll do is compare this to a set of standard curves for STC that are developed by ASTM, a standards organization. And from that, we get, or we derive, an STC value. So they might say something like, well, the STC curve for, 35, looks like this or something, all right? As an example. So we understand it's not going to be perfect. It's not going to be a perfect fit. But I'll tell you this right up front. If you have an STC variance of, 1 or 2, basically 1 or 2 dB is the way to think of it, you're not really going to hear much difference. It's, I'm not saying that they're going to be identical, but practically speaking, in typical sorts of situations, you're not going to be able to tell the difference between a barrier like a wall that's an STC of 35 and one that's 36 and a half. They're going to basically perform the same way. Okay, if they have similar construction, the effect is going to be the same. So you're not going to sit here and worry about 1 dB, right? You're going to look at some bigger numbers. If you have an STC of 20 compared to 35, yeah, that's something. Or 35 compared to 50, that's major. Now remember, this is dB. So doubling the STC is not a linear thing. That's a logarithmic thing. Okay? So what sorts of things get you a good STC? Well, like I said, mass. You have something that's very massive, or something that's absorptive, right? That can turn that acoustic energy into essentially heat energy at the microscopic level, right? What are some typical numbers? What can we expect? Okay, so, if you're looking at an STC of, let's say, 20, that's like hardly doing anything. If you're on one side of this wall and it's got an STC of 20, you can hear stuff pretty well on the other side. If somebody's having a conversation on this side, you're going to hear it on this side. Now, when you get up to something like, the 35 that I threw out here, well, you'll be able to tell that people are having a conversation on the other side, but it's going to be muffled. It's not going to be that intelligible. When you get up to maybe 45, it's just going to be sort of a dull roar that you're going to hear. Yeah, there's something going on the other side of the wall. I can't quite tell what it is. When you get up to maybe, 60, 70, well, now you're approaching an area that some people would mistakenly call soundproof, right? Like I said, there is no such thing as soundproof. But the loss is so great that you may not even be able to tell that people are yelling over here, right? I got people over here yelling, and on this side, you can't hear it, right? Because you got an STC of 65 on this barrier, all right? Okay, so, what would sort of typical numbers be for, real world things? Okay, so if we're looking at something small, like 15, 20, maybe, an interior door in a home. Lightweight hollow core door. There's probably a decent sized gap at the bottom, to swing. The jamb around the door is not very tightly sealed. So, I don't know, if you're lucky, maybe 20 STC. Compare that to an exterior door. Now you're looking at something that's got weather stripping. It's got a good bit of mass. That might be up around 35. Okay. An exterior window in your home. Again, depending on construction, single glaze, double glaze, so on and so forth, you might be looking, say, 25 to 30 for an STC. You can find them a little bit better than that, but, so let's say 30-ish for a good quality window, 27, something up in that range. Like I said, you're not going to hear a difference between a window that's rated at 27 and one that's rated at 29 for the most part. All right. Okay. What about walls? So a standard, let's say 2x4 interior wall, you're probably looking at, again, depending, do you have 1/2 inch or 5/8 inch drywall on it, stuff like that. you're probably looking at somewhere maybe 35 if you're lucky, 30 to 35, let's say, for an STC. And like I said, when you're up around this value, 35, okay, somebody can be in the other space and you can tell that they're having a conversation. You just can't hear it very well, right? These are going to be insufficient if you're really looking to make something that has some acoustic isolation. You have, maybe a home theater room that you're trying to build, okay? You don't want that sound to bother anybody else in the house or certainly anybody outside. Maybe you have a music room. You have a home recording studio kind of thing, right? Same deal. You don't want to bother people elsewhere. And, as I mentioned, you don't want the external sound, the trucks and buses and airplanes and so forth, having that sound leak in, and ruin, recording that you have. What are we going to do there? Well, you could think, let's go crazy, and maybe I'll get an 8x8 cinder block wall. That's pretty massive, right? So if you got a cinder block wall and you filled the gaps, like you put sand in the gaps, right? You might be looking at an STC of 50, maybe 55, something up there, all depending on the construction. Okay, that's really good as far as sound isolation is concerned. It's way better than your standard wall. But let's be honest. A cinder block wall is massive. Structurally, supporting that can be a problem. Can be expensive. There's a lot of issues there. So, typically, if you're going to make something like a home media room or something like that, we wouldn't do that. Or a home recording studio, we wouldn't do that. We would usually go with a double wall. Like, we would use maybe a 2x6 double wall. And I'll explain what that is in just a sec. But if it's done right, you can be looking at an STC of 60 to maybe 65. And that's fantastic. If you get numbers like that, you could have, let's say, in the studio, right? We'll kind of do it this way. So we'll say this is your studio over here. You could have sound pressure levels in here that are, 100 dB SPL. In other words, pretty darn loud. And you're only looking at maybe, mid 30s out here, which is probably going to be swamped out by the ambient noise. If this was outside, for example, nobody's going to hear this, right? And if you have loud sounds out here, on the street, you got a reduction of 60 to 65 dB on average into the studio, you're not going to hear it, okay? All right, so what is a 2x6 double wall? All right. We're going to take a closer look at this in a future video, but I'll just do this real quick. So I'm looking down on the wall. So this would be the plate. And the studs are coming up at you. All right, so these little X's, these are the studs. I'm just going to put 3 framing studs coming up. So normally you would just have this and you'd have a layer of, one layer of drywall, right, on the inside, maybe a plywood or a composite on the outside. Well, what we're going to do is we're going to make 2 walls. And we are going to separate these walls by maybe an inch or 2. So let's say, 3-4 centimeters. And those studs, those framing studs going up, are going to be offset. So they don't line up. Okay? And in this space, change color over here, in this space, because you got a 6-inch space in here, almost, you are going to put some insulation, fiberglass insulation. And then on the outside, instead of just putting 1 layer of drywall, and you do this to both sides, you could put 2 layers or 4 layers, right? And to make it even extra special, in between these, we will put in a viscous damping compound. So this would be something you would apply with like a caulking gun, right? You would put up the first layer of drywall and then you would squirt this viscous stuff all over it. And Then you would apply the second layer of drywall, and you would stagger them so that the seams don't line up, right? And what happens with the damping material is it basically turns the impinging sound wave that's coming in here, it turns this into a shear force. So this is, you could kind of think of this as like a gooey, sort of gluey, rubbery kind of thing. It never dries fully, right? So the sound comes in and you create this little shear force in here, and that absorbs a lot of sound, right? So this winds up giving you a fairly thick wall. You have a wall that's, at least a foot thick, but you get an STC of, 60, 65 out of it. But you have to be really careful. You can ruin this with little gaps and holes and things. If you aren't careful with sealing this, a little, what might seem like an inconsequential little crack or a pinhole is terrible. Just imagine having like a heavyweight, plastic bag filled with water. All it takes is one pinhole, and that water is going to come gushing out. All right, that water is going to escape. So it's the same thing with sound. This thing has to be really solid. All the gaps. That's why I said the joints on the drywall, you want to overlap those. You do something like this, and like I said, you're going to have really, really good sound isolation. Not soundproof, but it is excellent sound isolation. All right. Okay, so that's how we sort of prevent sound, or how we can quantify how well sound is transmitted through the barrier. And by the way, if you're thinking, what do I do about my windows? Right? Because I'm not going to just make a room without windows, my home theater, maybe in your basement, if you have a basement. But what do I do about that? Well, there are things you can do about that, and we'll look at that in a future video. Anyway, in part 2, we are going to take a look at the reflected part of RAT and see what happens there. Alrighty? Okay, so until next time, take care. Have a good one.